Hello friends, greetings from Professor M.I. Vyas. I am Associate Professor, Government Engineering College, Modasa. We have already started the properties of gas. We have learned certain areas, certain points, or we can say the certain aspects of the properties of gas. We have started with the vapor and gas. We have started the properties of gas. We have seen vapor and gas. What is vapor? What is gas? We have also seen the Boyle's law, the Child's law. Based on that, combined gas law we have seen. Then we learn about the specific heat. The specific heat for gas, how it differs from the solid and liquids. When we are talking the specific heat of a gas, we consider specific heat at a constant pressure, that is Cp, and specific heat at a constant volume, that is Cv. Then we also learn the Avogadro's hypothesis and the gas constant. Based on all this learning, we have established the relationship between Cp and Cv. Then we have started the non-flow process. In non-flow process, last time we have seen the constant volume process, where in constant volume process we have studied the relationship between PV and T, the work done, the heat transfer, the change in internal energy and the change in enthalpy. All these 5 points we learned in the context of constant volume process. Today we will do a very small exercise on this constant volume process, and then we further look into some more non-flow processes. Let us see small exercise. In a closed cylindrical vessels having a diameter of 1 meter and length 5 meter, the gas inside has a pressure of 100 kilopascal and 30 degrees centigrade. To increase the gas pressure up to 150 kilopascal, how much heat is needed? Take the Cp is equal to 14.307 kilojoule per kg Kelvin and Cv is equal to 10.183 kilojoule per kg Kelvin. C. So what it is given? The closed cylindrical vessels, pressure increases, volume remains constant. To increase this gas pressure, some heat we are supplying. How much heat we have supplied, that we have to find out. The values of specific heat for the gas is given. So let us start to solve these numerical problems based on constant volume process. What is given data? Given data is diameter 1 meter, length is given 5 meter, pressure at the beginning of the process, that is P1, 100 kilopascal, so it is 100 into 10 raised to 3 Pascal. Temperature is also given at the beginning, 30 degrees centigrade, so it is 30 plus 273 is equal to 303 Kelvin. Pressure at the end of the process P2 is given 150 kilopascal, that is equal to 150 into 10 raised to 3 Pascal. The values of Cp 14.307 kilojoule per kg Kelvin and Cv is equal to 10.183 kilojoule per kg Kelvin. This is pressure volume plot, pressure volume diagram, where this is the process starts from point 1, it ends to the point 2. It is constant volume process. V1 is equal to V2. We are interested that how much heat is supplied. How much heat is supplied in order to raise the pressure from P1, that is 100 kilopascal, to P2, 150 kilopascal. Friends, V1 is equal to V2. On PV plot, process starts from point 1 to point 2. Volume remains constant. V1 is equal to V2. Pressure increases. Pressure increases how much? From P1 to P2. To raise this pressure, we are supplying the amount of heat Q to the system. Amount of heat we are supplying Q to the systems. So, when V1 is equal to V2, constant volume, our relationship is P1 upon T1 is equal to P2 upon T2. So, you can find out T2 is equal to P2 into T1 upon P1. T2 is equal to, we are interested, T2 is equal to P2 into T1 upon P1. So, it is 150 multiplied by 10 raised to 3 Pascal. 150 into 10 raised to 3 Pascal, the values of P2 into temperature we had with us T1 303. P1 with us it is 110 into 10 raised to 3 Pascal. This gives you T2 is equal to 454.5 Kelvin. 454.5 Kelvin. Now you have R. R is equal to Cp minus Cv. R is equal to Cp minus Cv. So it is equal to 14.307 minus 10.183. This gives you R is equal to 4.124. R is equal to 4.124 kilojoule per kg Kelvin. Now, You know the characteristics gas equations. The characteristics gas equation is what? P1 into V1 is equal to MR T1. P1 into V1 is equal to MR T1. From this characteristics gas equation, mass you can find out M is equal to P1 V1 upon RT1. P1 V1 upon RT1. This is equal to initial pressure we had with us 100 into 10 raised to 3 Pascal. Volume V1. Now it is, the volume V1 is not given. How will you find out the volume V1? It is given the closed vessel's dimensions. This is the dimensions of the closed vessel. It is given. Length and diameter is given. You can easily find out the volume. You can take volume V is equal to pi by 4 into d square into L. So, you can put here that pi by 4, d is given 1 meter square and L is given 5 meter. Divided by R you have already find out 4.124, that is in a kilojoule. Friends, here it is given the R in kilojoule. When you are solving the problem, you have to take R in joule. So multiply this with 10 raised to 3. The R value is in kilojoule. When you are solving the problem, put this R value in joule. So it is 4.124 into 10 raised to 3 multiplied by 303. So you will get M is equal to 0.314 kg. This gives you the value M is equal to 0.314 kg. Now, for constant volume process, for constant volume process, heat supplied that is equal to Q, that is equal to M into CV T2 minus T1, M into CV T2 minus T1. Therefore, Q is equal to M. M is 0.314 into CV is given 10.183, and in our case the T2 is 454.5, T1 is 303. T1 is 303. So Q is equal to 484.187 kilojoule. 484.187 kilojoule. . This is answer. This is answer. So friends, we have done a small exercise based on constant volume process of the given data. We move further to the next process, that is called constant pressure process. The more under the non-flow process, another process is constant pressure process. We will see how this constant pressure process goes on. It is constant pressure process. Constant pressure process. So, in a constant pressure process, first we will understand on the PV diagram. On PV diagram. This is P, this is V, volume. The process starts from this point. Let us say it is point 1, 2. At the end of the process, it is point 2. Pressure remains constant, so it is P1 is equal to P2. Initially, the volume is V1. The volume is V1 at point 1. At point 2, it is the volume at V2. It is the volume at V2. Friends, this is the iso pressure process. As last time I told that this constant pressure process, so iso word is used for the constant, which is the properties remain during the process. So this constant pressure process is known as isobaric process. It is known as isobaric process. It is isobaric process because the pressure remains constant. Now we are interested to establish the relationship in PVT, relationship between P, V and T. So let us see that you know the beginning of the process, that is point 1. It is P1 V1 upon T1, right? At the end of the process, point 2, you can write down P2 V2 T2. This equal to, here P1 is equal to P2. The P remains constant, P1 is equal to P2. So in relationship you can write down V1 upon T1 is equal to V2 upon T2. V1 upon T1 is equal to V2 upon T2. Next, we are interested in the work done. This is our first point. Under this constant pressure process or isobaric process, the relationship of P, V and T. Next, we are interested in work done. We are interested in work done during the process. Work done during the process is nothing but the area under this line 1, 2. The area under this 1, 2, this is nothing but the work done. This is nothing but the work done. So that you can get work done is equal to PdV integral from V1 to V2, integral from V1 to V2. This gives you P, pressure remains constant, V2 minus V1. Work is P into V2 minus V1. Then we are interested in the change in internal energy. We are interested in the third point. Under this process, we are focusing on change in internal energy. The change in internal energy is it is functions of temperature alone. So you can write down the change in internal energy, that is du is equal to m into Cv into T2 minus T1 into T2 minus T1. This is the change in internal energy for the case of constant pressure process. Then another aspects that we want to learn: heat transfer. Heat transfer. So that last time we have seen that we can use the first law of thermodynamics, which says that change in heat is equal to the change in work plus change in internal energy. The work you have already defined, P into V2 minus V1. We have already obtained the change or the work done is V2 minus V1. Or you also know the change in internal energy is equal to M into Cv T2 minus T1. M into Cv T2 minus T1. This comes P V2 minus V1 is nothing but M R T2 minus T1, M R T2 minus T1 plus it is M C into Cv into T2 minus T1. You can use that R is equal to Cp minus C1. Here put the value R is equal to Cp minus C1, Cv, Cp minus Cv. So this is what M into Cp minus Cv T2 minus T1 plus M into Cv T2 minus T1. If we open this Cp minus Cv T2 minus T1, M CbT2 minus T1 minus here plus M CbT2 minus T1 will be cancelled out this with this one. The only left out change in heat transfer, this heat transfer, change in heat is equal to M into Cp into T2 minus T1. M into Cp T2 minus T1. This is the change in heat transfer. And the last we are interested in the change in enthalpy. Change in enthalpy. Change in enthalpy that in case if we refer the constant volume process, that change in enthalpy, we have started with that H is equal to U plus PV. So we put here for 0.1 and 0.2, if you put the values, and the way we go in constant volume process as per constant volume process, you will get change in enthalpy is equal to delta H M into Cp T2 minus T1 M into Cp T2 minus T1. The exercise to reach to these equations that I have not done over here, you can start the way we done in constant volume process. You can start that the way we done in constant volume process from point 1, point 2, use this equation H is equal to U plus PV. You do on your own and reach to this. We are moving to a small exercise of this constant pressure process. A constant pressure, air is heated in a vessels from an initial volume of 0.5 meter cube to the final volume of 1.3 meter cube. Determine the heat supplied, work done, and initial and final temperature of the air for 10 kg of mass. For 10 kg of mass. We will solve this numerical problem based on our learning of constant pressure process. So the data given. So the data given. Mass is given 10 kg. Volume V1 is given 0.5 meter cube. Volume V2 is given 1.3 meter cube. It is constant pressure process. P1 is equal to P2. That is the process carried out at a 5 bar pressure. So you can write down that if you want to convert, that is 5 into 10 raised to 5 Newton per meter square. Now you have with characteristics gas equations, that is P1 into V1 is equal to mR T1. P1 into V1 is equal to mR T1. You put the value 5 into 10 raised to 5, that is pressure. Volume is given 0.5 is equal to mass is given 10. The data you can take that R is equal to 0.287 kilojoule per kg Kelvin, and take Cp of gas is 1.005 kilojoule per kg Kelvin. This is the part of data. So 10 into 0.287 into T1. By calculating, you will reach the T1 is equal to 87.10 Kelvin. T1 is equal to 87.10 Kelvin. Now for constant pressure process, constant pressure process, you have a relationship with you V1 upon T1 is equal to V2 upon T2. You have already find out T1, you had with you V1 and V2. By putting the values, you will get T2 is equal to 226.48 Kelvin. Heat supplied is equal to Q is equal to mCp T2 minus T1. So is equal to 10 to 1.005 into T2 226.48 minus 87.10. You do this 10 into 1.005, 226.48 minus 87. You do this calculation on your own and find out the answer. It is, I am leaving up to you. Then you find out the work done. The work done is nothing but P into V2 minus V1. Pressure is given 5 bar pressure. So 5 into 10 raised to 5 Newton per meter square. Volume V2 is given 1.3. V1 is given 0.5. This comes to you 400 kilojoule. Work done is 400 kilojoule. So friends, what we have done, we have done the exercise, small exercise for the constant volume process. We have seen how to use the theoretical concepts in this numerical problem. Then we studied the constant pressure process where pressure remains constant. We see the relationship between P, V and T. Then the work done. Then the heat transfer, change in enthalpy and change in internal energy. We have also done the exercise based on constant pressure process. There are few more processes left out that we will see in continuations in a next lectures. I advise you to see the good books, do more and more practice on this theoretical part which we have seen. Till then, a very best of luck, happy time to all of you from Professor M.I. Vyas. Thank you.